Okay, so with this and any of the other classifications that you use, um, you do have to run it on data that currently doesn't have seagrass. And the reason that I was like, oh, we need to take a break here, was it didn't end up actually being a real reason. I forgot. So your your data that you train on is your training data, and the data that you classify on is your global data set. And your training data and your global data set need to have the same fields. And I was like, oh no, I did that filled thing, which replaced all the fields. But I don't know why I just had a brain hiccup. That original data set, this data set that we created, this EMU global FMV data set, has all the same fields. Remember? Yeah, so I didn't actually need to do anything. So during the break, all I did was run the data set with that. So the only difference, you still actually use the same tool for running your your thing. So this is the output. But the only difference is that it's not in train only. It's in predict to features mode. So you put it in predict to features mode. If you trained it using features, you put in your predict to features mode. If you trained it using rasters, you put in your predict to raster. You put it in predict to raster mode. But we're not covering raster in this course. But basically, you always actually train it with features. But the features represent like a polygon over a certain area within a raster, and what it does is it calculates the value inside that raster. But this isn't really a course about that. It basically calculates. It's kind of like doing zonal statistics. If for those of you who've taken a raster course before, if you choose predict to raster, your polygons need a raster underneath them, and it does zonal statistics on those, and then it classifies those zonal statistics. That's the table it uses for the classification. Okay. All right, so we're just going to leave all the others the same and say predict to features.
Is that Antarctica, that line straight at the bottom?
What's that?
The picture itself, is that Antarctica, those dots?
What dots?
Below Africa and all these other things.
Yes, Antarctica. Sorry. I thought you said an article, and I was like trying to think of which article I talked about that talked about the thing.
So I was assuming it would be seagrass above and below, but it is based on that model.
Yeah. So when we run the model, all I did was the other besides predictive features, when you say train only, which is the mode we ran into before, there was no outputs. Remember, we didn't create any outputs. We just saw the result. But if you want to actually see the result, you'll do predict to features. And it runs faster if you don't have this selected. That's why there's a train only option. So with the train to, what do we need to do for our predicted features? What do those need to be? Those need to be the EMU global FMV data. That's the data that has the same fields in it. So your features need to have the same fields in it. Okay. And then you can tell it where you want it to be saved. I'm just going to call this EMU global underscore FMV underscore trained, which is what I called it. So I already ran this once. So when I hit run, now I did it like the cooking show.
That's the global one that you're running, right?
Yep. So I ran it, and this is the result. So this is the result. So what do the pink colors mean? Well, pink means that the model predicted that it could be seagrass habitat. No means that the model predicted that it's not seagrass habitat. Okay. So that's what it did.
So how can we check the accuracy of this?
Yeah, so we would have to have a data set that we could go in, and how would we actually do that? Let's say we had a global data set of seagrass polygons. I don't know if that exists. What's that?
Will you run on the global first if you had one? to do it global when first instead of the United States, wouldn't you have done it like that?
I mean, but
If you have a global data set, what's the point of predicting?
if you have a global data set, what's the point of predicting? Exactly.
But if you had a global data set in the United States,
If this was like a
Yeah, this is the data
project,
set that.
you could go to different places and test it and see if it's right. Not like randomly select locations and go.
actual sample locations.
Well, this is the data set that I used to make the model, the seagrasses in the United States. So, yeah, so what I could do is, if we had a global seagrass layer, which I'm sure exists somewhere, but it's not in ESR's Living Atlas data. But if we had that, we could use that to check the data. But if we had that, why are we creating it in the first place, right? Or maybe we're updating it, or maybe we're making a better one. Who knows? But for whatever reason, we don't have everything. And so this gets into the concept of sampling, which is a statistical concept. So we could hire some students to go look at high resolution imagery, zoom in, and delineate some areas that were definitely seagrass. And we could call those areas like our samples. Now, theoretically, if we did this, we would want to make sure that we did this everywhere in the world, that we didn't just do it in certain places. And we could then use that data and come up with the validation and say, okay, well, 80% of the time when they said there was no seagrass, there really was seagrass. How do we do that? Well, we could bring up all of our points in GIS, and our points probably wouldn't be exactly the same location because we've used these 90-meter points. They're pretty far away from each other. But we could say, okay, we're going to decide that it's the closest point to that point. Okay. And how far off is it? Is it yes or is it no? So that's how we would do that. You'd have to have that third data set that I talked about, your validation data set. And it does create, so the real work in this whole process is really the training data, creating the training data, and creating the validation data set. That's where the real work comes in. Okay, you're going to have to run it in the GIS, but creating those data sets takes time. So the second step takes know-how to know how to do it, but it doesn't consume a lot of time. But when you were getting at that example before about the stop signs, right? There are also, like, if you go read online, like automatic detection of automobiles in imagery, okay, or buses. Like there's all sorts of people researching, just like trying to find if a bus is an image, which it's really the same problem here. You could even use this same tool to do that. It's not the best tool for it, but it's a tool that would work for that sort of thing. So you would just have to boil your data down into having observations with answers and observations without answers, and then withheld observations also with answers. And those are the three: the testing, the training data, the global data set that you're trying to find out, and then your validation data set. So you need those three data sets. Sometimes you can actually create in fact, a lot of times, you create the training data and the validation data. You create it at the same time, but you subset it out and say, okay, this will be my training and this will be my validation data. Your training data and your validation data cannot be the same.
Right.
They can't be the same data set. So.
Because you don't get the same answer.
Right. Yep. All right. And actually, if you did have a big enough training data set, we could actually do the validation right here in this step. If we can make this a number that represented a significantly high amount of people, that's an acceptable validation right there. But ours was so tiny because we didn't have enough data that we didn't want to do that. So, I mean, just looking at this model, It does look like there's plenty of error, if you will. Like I know that there's probably seagrass on the west of the east coast here of South America, but this looks like it overpredicted a lot of seagrass areas.
So the training variable that you give it, where do you ever have a large number of those to say that it's not?
You should have a large number of training data. Yeah. I do know that there is a fair bit of seagrass up here, but don't know if it's quite that widespread.
And what we did with the melting of the ice and all the pollution of the ocean, let's kill off a lot of the data that we got, because a lot of things change at such a global level there.
Well, yeah, I mean, you'd want to run this temporally to see, you know. This is a way to examine your data on kind of like a big scale and to see general patterns. But you still want to have scientists out studying, you know, individual places. They could look at something like this and decide areas that they might want to study a little bit more. All right. So I have this other data set here. I think I created way too many points. What I'm trying to do, because my goal here is to show this other concept of basically I want to be able to take data that has a bunch of attributes, and then I want to divide them up into categories, but I don't necessarily know what those categories are. One word for this is unsupervised classification. So supervised classification, you need a training data set, and then you give it the categories in the training data set, and it runs, and it looks for patterns in your data that can explain those categories that you created. So unsupervised classification, it still starts with putting everything in that three-dimensional or x-dimensional space, n-dimensional space is a better way to say it, and it looks for ways to categorize the data so that they form more or less little clusters in three-dimensional space. We're not talking about clusters spatially like we did earlier in the semester. We're talking about, do they share similar attributes? Are they similar? And so what I want to do to demonstrate that is I've got this climate data. This is a data set I use a lot for different examples. Make sure I'm recording here. I've got this climate data, and the climate data has temperature and precipitation. So if I'm interested in kind of categorizing areas by their monthly temperature and precipitation averages, you know, then I'm going. This might be a thing that I would do. Like, I'm gonna take the entire United States and find out which areas are similar. Like, have you guys maybe traveled around the United States, or maybe you haven't? But is there an area that you know of in the United States that has a similar climate? Well, Alabama does, right? Because it's right next to Mississippi. But how similar is the climate, you know, in these mountains to these mountains? Do they share some similarities? And so this would answer that question. Is we could take the entire United States, and with unsupervised classification, you do need to decide beforehand how many classes there are going to be. How many classes am I going to create? So you could say, I'm going to divide the United States up into 4 climate categories, and those 4 climate categories, what it's going to do with your data is decide in three-dimensional, or in this case, n-dimensional space, which data has the most similar values for temperature and precipitation in space. But first of all, we need to get some points to some data and some locations to do that. And right now, I did all these. I'm not sure if this is going to create. Let's see how long this takes to run, and if it takes a long time, then we'll do smaller hexagons. So I alluded that I was going to show you this before, but you can extract values to points. So extract values to points will take the value in a raster and put it in a point data set. So I'm going to take my features, which are points, and I'm going to take my climate data, and I'm going to extract those values. Now, I don't know, because my climate data, I have one data set called climate data that has every single precipitation and temperature value listed. Let's see if this works. Or if it only gives me the top data set. Actually, you know what? I think it's just going to give me the three.
So you got to compare them based on the same traits, so you can come out.
Hold on a second. Is this even starting to run? Yeah. Is there a way to cancel this? Because I don't think that's gonna. I think it's gonna take forever to load. Because it hasn't even started running yet. Yeah, let's just close that down. I think I succeeded in freezing out my computer totally.
You gonna use the same forest-based calculator?
No. In fact, well, does this one still work? So under, if you go to toolboxes, so this one will still work. So I'll talk about it from here. So if you go under the spatial statistics tools, there's one under. It's not. These are what we already talked about. Oh no, sorry, just the bottom half of these. So in fact, specifically, we'll talk about multivariate clustering and spatially constrained multivariate clustering. So these ones up here, well, actually, outlier, hotspot, and cluster and outlier, those are what we talked about earlier. And those are more dealing with identifying spatial clusters, things that are nearby each other that have similar values. And multivariate clustering, what it does is it tries to, well, multivariate clustering might as well be called unsupervised classification. What it does is it finds clusters in feature space. In other words, let's just say we had a scatter plot, just a two-dimensional scatter plot, X and Y. We have temperature and precipitation, and we have all of those points in the United States. What's their temperature and what's their precipitation? Well, if they're nearby each other, what does that mean? That they have similar temperature and precipitation values, even if they're not actually nearby each other. They might be all the way across the other part of the country, but they have a similar temperature and precipitation value. And so clustering in feature space is sometimes called unsupervised classification. It's saying, okay, all these points are nearby each other.
We're clustering in features.
Oh, it finished. Okay. Yeah, it just pulled out one raster value, I think. All those are null. Okay, I got a better idea. So what I really want to do is delete all these. And again, we're just going to do this with way less data points, which I think is fine. But it'll be better for a class. But what is the lab where we did... I think we... Yep. Actually, we could... Let's bring this... Well, I'll bring that in on a different map. So I've got my USA contiguous. All right, so I got all my hexagons, and I want to change those hexagons into points, just because it's going to be faster if they're points. And then I'll run that, and so that way I can pull out the temperature and precipitation values from all those points. While that's running, I'm going to add some data into a new map, and I'm going to give a more socioeconomic. Well, here we'll do on this one. Well, that one's running. Insert new map. Okay, so we got this other map, and we're going to add the county health ranking data that we used before. Remember that? What lab was that? I guess it was week 7. So we have our county health ranking data, and remember, it had a bunch of attributes that might be helpful. Right, it had diabetes, patients receiving, I don't even know what that is. You guys know what that? Preventable hospital stays, Medicare enrollees.
You know where that data came from? That helped?
Yeah, I got this from the Living Atlas.
Okay.
Yeah, you can just Living Atlas, Google. It's called county health rankings or county health data rankings, maybe. So I got unemployed, labor force, percent unemployed, and when we do this, you have to think about sometimes that the data has to be normalized. So when we're talking about building clusters of similar things, would it be better to use unemployed or percent unemployed? So what if a county has 100 unemployed people, but there's only 1,000 people that live there, and another county has 100 unemployment, but there's 2,000 that live there? Are those counties similar at all in terms of their unemployment?
Not really.
No, but they both have 100 people unemployed, but that's not really that important, is it? So sometimes you need to think about what makes this value similar to another place. And if it needs to be normalized, you need to normalize it. So I'm going to cluster this data, but I need to pick variables that make sense. I can't pick unemployed because unemployed is yeah, because it's not fair if 5 people are unemployed in Sunflower County, Mississippi, but there's only 20,000 people or whatever. I mean, it's totally different.
And there's 5 unemployed in Clovis seats.
Yeah, it's way different.
So you got to think this stuff out. So when you try to put it together, you got to think about it.
So using like an unemployed per percent or an income, a percent income, that would be called normalizing your data.
Yes.
Okay.
So normalizing your data means to adjust the data so that it fairly represents the variable that you're trying to get across. And so lots of times that means dividing it by either the population. Sometimes it's dividing it by the area. Like if it's something that you think should be compared as to how it distributes across the landscape, then you should say, well, it needs to be the total divided by the area. Okay. Like, well, if there's like some pollution, it's like, so some amount of pollution that's happening, you don't want that to be like, if you have, well, if all your units are the same size, it doesn't matter as much, but let's say the total amount of pollution that's occurring in some huge county out west versus the total amount of pollution that's occurring in some small county here, those are different things because they're different sized counties. Okay, so here we've got the county health rankings. And remember, what's going to happen is we're going to divide the United States up into similar categories. And let's just check most of these boxes that make sense. So if we say years of potential life lost and percent fair, healthy, percent physically, those are just days. Okay, percent smokers, percent obese.
If you use percent for one, you should use percent for all.
Yes, percent effective drinking, driving deaths.
Physically
Well, that's not. That needs to be percent driving dis. Did I do what?
Oh, the same percent.
Oh, that's
physically
percent
inactive.
physically. Percent with access to exercise opportunities. Teen birth rate is still a rate, so it's divided by people. It might be out of 1,000, but still uninsured. Oh no, sorry. Percent uninsured. County size, is that even on there? I don't know if that's important.
I don't know if it's, I mean, the square.
I think the population would be more important for this stuff.
Okay.
Well, you know, like you say, all of them got marriage distance, so none of them don't have no.
Diabetes.
Right.
They have in common.
All right.
One might be big another one, but
Graduation rate. Okay. So I selected a bunch of these things. Percent unemployed. That's probably enough. Okay. I selected a bunch of those things. Ideally, you want them to be kind of similar. Okay. And so there are actually, there's actually a drop down here for the clustering method. The default is k-means. It's a very common way to do clustering. So what it does is that you specify the number of clusters, and for some reason the denotation there is k. So we're going to specify the number of clusters, and let's say we want 10 classes. That's what it's going to be, 10 classes. And what it does is it takes your data, and for however many variables you select here, you might select 100 variables, you might select 5 variables. However many you select, it takes those 5 variables, and in 3-dimensional space, it distributes, or 5-dimensional space, it distributes a bunch of values in there, and then it calculates for the nearest neighbor, it calculates the average of all of the values. Okay, and then it moves around, so it does that over and over again, and every time it does it, it moves to the mean. It moves to the true mean of all the nearest neighbors, and it keeps doing that, okay, until it stops moving as much, and that's how it works. So I shouldn't draw on a board, but because you wouldn't be able to see, but yeah, so yeah, it's just repeating that a certain number of times. Right. So if you select optimized seed location, it's going to put those just kind of distributed evenly through the thing. So we're going to run this, and what it's going to do is, well, first of all, it's telling us that there's some features that have bad records. So what it's going to do is it's going to let's make this bigger. It ran through, and these are the classes that created. What does class 1 mean? What does class 2 mean? What does class 3 mean?
Is that the highest and lowest?
No.
Know yet.
We don't actually know. It just found counties that had similar values for the boxes that we checked. Yeah, so Envy has a tool that does this exact same thing. I think in Envy it's called unsupervised classification. Yeah, so ISO data is another clustering method that's actually really similar to k-means. It works a very, very similar way.
So it's isolating certain things with another.
Yeah, so it's identifying. So what we can do, we don't know how, but these counties all have a value of 10, and these values all have a value of 10. So what can we infer about these 3 counties on the coast of Florida and these 3 counties on the coast of the United States?
They have something in common.
They have something in common in those values that we checked. So in other words, they all had to do with health. So all of those counties have they share a certain aspect of their health.
Look at Texas, sticks out in
Can
yellow.
you click those
They all
colors?
something bad in Texas.
Right, actually it looks a lot like rural Texas is all very, very similar. Yeah.
Can you click those colors and it tell you what's there?
Or what's similar?
Well, it can tell me it can tell me what class it had. Let's look at the. So what it does is for each one, it tells me the values that were the input, and then it tells me the cluster that it produced. And so I could do zonal statistics on each of these, or I mean, for those of you you're in this other class, I could bring it into a pandas data frame and do a box plot on all 10 of these, but by doing a group by and then create a box plot. And then I would see the range for each of these values for each one, and then use that as a way to say, okay, well, I'm going to interpret this class as meaning this thing.
As meaning low income or high diabetes or whatever
Right.
it is.
Yep.
So like if you only selected like 2 fields, in the analysis fields, and you only ended up getting like 2,
It's still going to try to find if you. Oh, you mean if I only choose two? Like, do you mean if I only made 2 classes instead of 10 classes?
Yeah, like if there's only 2, if you run it, you only get 2 classes. Would that mean that there's a low correlation between those 2 things, or how exactly?
You choose how many classes there are.
Okay.
So you get to choose how much classes there are, and you can use other tools to see how much. There might be a little bit in the report to see how much correlation there is between the different layers. Yeah. So. Yeah, that's just the mean of each field. So that's not really important summary. So you'd have to do something like examine the data using some other tool, or even you would use in ArcGIS. It would take a lot longer than it would if you programmed a script to do it, but you could examine the values for all the yellow ones and all the green ones. So health-wise, it looks like Lamar County is in this light blue or dark blue, and it looks like the coast has 2 of the orange counties and 1 light blue county. I don't see a whole lot.
What would be a tool that we could use?
These are all orange actually out here. This is the same color as the coast for some reason. So you share similar health values to New Mexico and things like that.
Oregon.
And Oregon. And yeah, looks like mostly rural Oregon, a little bit of coastal.
So what would be some of the tools that we could use to figure out why all of Texas is yellow, or rural Texas, or west eastern Texas?
Can you hotspot that data too, or is this a hotspot clustering to see? But that's not what we're looking for, right?
Well, I mean, it depends on what you're looking for.
Oh, but those charts show it that produce underneath the thing?
What's that?
See, underneath.
Oh, yeah.
Those charts, would those show it?
Those have some information, yeah. Oh, there's the box plots.
Put it down there.
Gotta make this bigger. How do I make this? Is it right there? All right, yeah. So this is a box plot of each one. Wish it was bigger. Zoom in on that. So it looks like. This is each class. So this is 10. So class 10, the one that was by the coast here. I think that was class 10. Yeah, the red class. See how it looks like it's a little bit higher than the other ones at diabetes. This might be better. This might be a little bit easier to just understand what's going on by just saying 3 classes, because we'll be able to see it a little bit better in the charts, right?
To be able to compare and stuff.
Yeah. So this is only producing 3 different categories, right? So maybe these are like unhealthy, middle of the road, and healthy and green. I don't know. If we could interpret them maybe that way. let's see.
So like if you go to your analysis field and you select like multiple things, how exactly is that going to affect how it's comparing, I guess?
Oh, if you select multiple ones of these?
Yeah.
Well, it's going to look for clusters in that many different dimensions.
Okay, so
I can't open
you
this
have
anymore.
like those 4 or 5 selected, then it's trying to find out where all of those things all happen in those locations.
Right. Yep.
Oh, no, it's just saying how much of each cluster.
Yeah, that's how many there are of each one.
So the largest is blue, but it looks like it's more stable, it's going straight to the middle.
Yeah, actually, the information in this box plot would be pretty good, but yeah. So if we zoom down in here, you could see that if we just kind of do high, medium, and low, the counties that are the red color have actually the lowest diabetes values, the lowest dental rates, the lowest graduation rates, the lowest percent excessive drinking, but they have the highest, oh, that's actually the opposite value. They also have the highest percent fair poor health. They have the highest percent obese, the highest physically active, the highest percent smokers. We got to go down here. They have the lowest people with access to exercise opportunities.
Okay.
So the red ones are the least healthy because they have the highest of all of those values. Now let's look at see if any of the. It looks like the green pretty much does the opposite of what the red does. So what it did was it created a cluster of healthy, unhealthy, and middle of the road. So the green is the most healthy areas according to this index. So actually, this is the way you've probably seen things where they say the so and so whatever index. And this is the way that those things get created is through using a tool like this, an unsupervised clustering tool. And this isn't the only unsupervised clustering tool, but it is the only one implemented in ArcGIS. And it is one of the very most common ones to do that. So that's.
So look in Texas, you can see the big cities that pop out in green. Like you have, it looks like Dallas in the top. You go over to Houston, like it's like the pop up.
And you could use this as like if you're writing an article or something, you could use this as evidence that that the text, because Texas does have some interesting demographic trends, and of all the places, the big cities in Texas are different than the country areas of Texas, right? Whereas in California, there's not as many big differences in the way that it goes. So.
And you can definitely like South Florida is a lot healthier than North Florida.
Right, healthier.
In the Panhandle, they got a little taste of apple.
Now I do want to run. There's another one right here. There's another tool called spatially constrained multivariate clustering. And what spatially constrained multivariate clustering will do is it actually does the same analysis, but what it does is the neighbors that the classes that you create have to touch. So, in other words, if you say there's only 3 classes, then it will find the 3 largest areas, and they can get pretty intricate, that are actually contiguous with each other, that share values. So you see how there's some like islands in here? See how these islands exist? And those are interesting. Really, there's probably not a reason why we want to get rid of those islands. But let's say we're just trying to develop a regional map that shows regional trends. Then we use the spatially constrained multivariate clustering, because what it'll do is it'll allow some places to go into categories that they're not in to make a an area that's totally compact. It doesn't touch. So in other words, if you were like, I mean, I don't know if you've seen these things, but like let's say you were, I don't know why you'd want to do this, but divide areas up regionally based on their health rankings. That would be silly. But like, let's say you want to divide areas up based on some other characteristic and put a regional office in each of those places, then you would run this because that's what it would do.
So if you ran something like this, those islands that pop up that are Texas's big cities would go away.
Right. Exactly.
Okay.
Yeah, I mean, depending on, you might get a little island, but anyway, so I don't know which all ones we selected before, but it doesn't really matter because this is homicide rate.
That's the only two differences between the multivariate clustering and the spatially constrained is that if each group has to be touching.
Right, they have to be touching, and so it'll compromise in terms of it looks at their. Basically, what it does is it includes space as another dimension, and that spatial relationship that must be considered. Okay, so I forgot all these, but percent fair poor health, percent low birth weight, percent obese, percent smokers. That's probably enough. Percent physically inactive. I don't see a percent uninsured. Okay, so now we're going to run this. You can say that your clusters have to be a certain size, otherwise they get merged in with other clusters. So you could say the smallest cluster has to be 5, or it has to have it can't have more than 1,000. So that's what that means. No, it's 5 features. It's the number of features. See the number of features? You could just say I want you to choose them. So you could say none. We could also say that we want to make it if we choose attribute value, if they share a similar attribute, they have to be in the same cluster.
So if you did pick 5, like Dallas and Fort Worth would go away because there's only 4 clusters, like 4 counties.
Mm-hmm. Yeah, it won't choose anything larger than that. So we're gonna say that the number of clusters this time will be, let's do 5 because it'll be a little bit, because when they're spatially clustered, they're already going to be more generalized. And so let's run that. Oh. Did I specify an output name? This failed. Oh. It says there are too many disconnected clusters to solve this model. So in other words, what it's saying is that that we just have too many like there's no way to fit them all together because there's too much differences. Maybe if we jack it up to 10, there'll be more. They'll be better. Well, is there a way to unselect all? Reset. So let's just select a few of these. Percent fair for health. Here's a potential loss life rate. Maybe just 2 of those and go back to 5 clusters. Maybe even 4 with just that little. All right, okay, there we go. So now these are based just on years of potential life lost and percent fair poor health. So it's saying that these areas are spatially clustered, and it actually threw out those the ones that are in yellow don't sorry, not yellow. Those that didn't even put in any cluster. So see how it didn't put these values kind of close to the border. All right. Yeah, West Virginia is like totally different than the rest of them in terms of those two values. I mean, it is kind of on the border there. Okay, but you know, we could come up with other ways to do this, but those are, I mean, sorry, not other ways, but we could come up with other examples. So my other example was going to be over here with the hexagons and the USA, right? So if I wanted to cluster the United States based on different climate zones, what I could do is extract values to points, take the points, and then I actually need to put in each of these. Oh, I chose the wrong one. Let's extract multi-values to points. So feature, and then I input the raster that I want to select. I'm going to see if it'll do this multi-band raster. I'm actually going to choose it on disk. So that was in here, climate data. Okay. I don't know if it'll pull out the data from every single one, but I'm going to test it out real quick. See if it does. And if it doesn't, I'll have to just kind of choose a few of the other values. So this is just another example. So in these cases where we're doing classification, the unsupervised nature of it means that we have to interpret the classes. We have to decide what those classes mean. But the advantage is that the computer has found areas that are very, very similar to those other areas. Like there's a mathematical reason why those two are being clustered together, because they share a similar value. All right. I pressed run, right? Okay. Once this runs, we'll have the data to run it. Hey Sarah, did Cochran, was he trying to ask me a question or something, or?
Oh no, he's just bugging me about a deadline I have.
Oh, okay.
Yeah.
Fun.
Saw the moment of opportunity and seized it.
I feel your pain on that one.
Yeah. I can't hide it.
Nope.
All right, here it is. It's almost ready. So this tool, extract multi-values to points, is a good one. If you have a bunch of rasters, but you want to sample them to get feature data out of it, you can do that. So now that one's complete, and I think, I'm almost positive that it does. Yes, good. So it has all of the data, both the climate data and the precipitation data. And if we go down here, there's less null values. Why? Well, it's because the null values are all the areas that aren't within the United States. Right, so I'm just going to go and select them all. It'll be faster if I do. Oops. So I sorted on that field. All the fields have the same null values because it's the same raster. And so I take those and I'm going to switch the selection and export features and call this good. Bad name, it says. Too many missing or no values. What? Oh, yeah. Oh, no, that was, sorry. So this will be good points.
I know, it is weird how some will make you add it on to your first name.
Right, and some put it in the output location.
I guess it depends on who made them, who designed them.
Yeah, who made the tool.
Mm-hmm.
Yeah, I mean, it used to be that they were all like this, and I knew why, because what you put here often depends on what the dot .shp or whether it's .tif, like, or whether it doesn't have an extension, because this determines if it's a folder or geodatabase or what it is, and then this then determines what the name's going to be. Sometimes the name that you put in there, it's required that it has a certain value. I wonder why some of these are selected. I guess they got the points because. I don't know if they. Well, now they all say no. Probably just because it's still running. Slow computer day. All right. Well.
What was funny is I was actually going to ask you yesterday what type of laptop you had.
Yeah, it's supposed to be like a awesome laptop. It was like over $2,000. I mean, I bought it on one of the projects, but yeah, it's got like, it doesn't have the very top of the line, Intel processor, but it has like the second highest, and then it's got like 32 gigs of memory, which is a heck of a lot of memory. Yeah.
Well, when it comes to laptops, they're by design, they're going to be slower than desktop equivalent. But your best bet for laptops, if you're going to be doing this kind of stuff, especially right now in the market, is to get, well, not necessarily a gaming one, but see, it's not that you get a gaming one is good or bad. All a gaming one's technically going to do better is like rendering 3D stuff, so it's got a dedicated graphics card. Okay? But as far as actually calculating data, that's very CPU intensive. And what you ideally want is a multi-core system. And right now, that's Radeon leading the charge in that, as far as laptops. It wasn't that way for a long time. Always. But right now, Radeon is really hardcore software, really good clock. What that's going to allow you to do is it's going to allow your system to more cores get things like more people working on the same project. Okay? But if there's not enough work being spread out, these are doing nothing. Okay?
Right.
So with this, if you have more different types of data all connected together at once, more cores with a factory base line, help you out a lot. Of course, RAM's still important. 32, that's where you want to be on the RAM on that. For this kind of stuff. But it's just going to come back to what your processor is capable of doing.
Yep. Okay, so once this runs through, we're going to run the same tool that we ran before, which is called the multivariate. I don't know where. Oh, I'm looking in history, not in toolboxes. Multivariate clustering is what it's called. That's what ESRI calls it. It's almost done. And then what we'll do is we'll put all these climate variables in. And the climate variables, do they need to be normalized? Not really, because this is temperature and precipitation. And so it's not totals, it's just the value at that point. And so what it's doing is looking for areas that have a similar climate, because these are actually yearly averages. Okay, so I've got my multivariate clustering, and I'll choose the good points, and I'm going to select everything. I'm going to take off the original FID. That should be good. K means how many clusters I think I might want to select. Everybody? 5? Sounds good. and we'll run that. And so now it should symbolize those. Once it finishes. Now with each of these, like if you'll notice here, when it ran, it saved them out to be a new file. So that's where it's putting it. And it's running a lot slower here than it was before. I mean, I think there's less points. Yeah, 1,743. How many counties are in the United States? Do you know? Yeah, there's like 3,000 counties. So this is actually less data than that was running in that other example. But it's gone back to being slow here for a second. I just realized I told somebody to do something after class yesterday and they didn't do it. All right, well, so I don't really have a lab for this data, but you have a few data sets I pointed out for this one. You have a few data sets you could use to do this. In fact, if I'll upload this data set after class, the points with the climate data associated with it. All right, so it just looks like it's just finishing up. And you could use it to do that. Let's see. There we go. Wait, what? Oh, I got to take the selection off.
It didn't run just on the selected points.
Well, I didn't. The selected points were the ones I wanted.
Oh, so it didn't matter.
It didn't matter. But there we go. All right. So there it is for the United States. So in terms of precipitation and temperature, yearly precipitation, because it's every month of the year. So January, February, March, April, May, June, July. And remember, this is actually multivariate clustering. So it's not, we didn't select the one that's spatially constrained one. So even though it wasn't spatially constrained, we could see that it's a lot more spatially constrained. So if there's only 5 classes in the United States, the whole Southeast kind of comes into the same category in terms of precipitation and temperature, as well as the Southwest, with just 5 classes.
You can definitely see that dry line in Texas.
Yeah.
The wet dry line.
Yeah.
It's super noticeable when you drive across country too. Like
where you driving around Texas?
It goes from like one thing to another.
So it's interesting. These alpine climates basically share a lot of similarities with these areas.
Is that based on the elevation of?
There's no elevation included in this. This is just precipitation and temperature.
Wouldn't that be, without showing it, without putting it in there, would it be maybe a factor that you guys can work in there? Because when they have
well, yeah, you could use that to explain why you see this pattern, but it wasn't used as a thing. So here's the box plots for that. So it looks like the yellows had almost the lowest the precipitation values, and then it looks like they had almost the highest temperature values. Throughout the year, they had the lowest and the highest. So those are warm, dry places. Whereas number 3, it had, which is the blue, the green. The green had the lowest precipitation and the second lowest temperatures. So those are cool, dry places on average. See that? Let's see if any of these cross over. So the blue and the purple cross over in what looks to be, because this starts in January, January, February, March, April, May, June, July, August, September. So the main difference between the blues and the purples in precipitation is that they have a slightly wetter summer. The blues have a slightly wetter summer. So the blues have a slightly wetter summer, where the purples, they're not quite as wet, and they're much cooler in the winter. See how much cooler they are? Yeah. So yep, and the purple. So we could run this again, because if we wanted to say, well, maybe we have more than that in terms of clusters. Maybe we have 10 different climates that we want to think about here in the United States. Whoops. That did take a little while to run last time, didn't it? Sorry. So maybe this will take a few minutes. Did I clear? I forgot whether I cleared the selection, because maybe that was causing it to take a little bit longer. But yeah, if you look at a climate map of the United States, the climates that take place on the coast are actually really thin. They only exist on the West Coast. They only exist right along the West Coast. So we might need to ramp up and get some more clusters to have those areas pop out as their own unique climate. Of course, it looks like the marine, the colder part of it did do that, but the warmer part of it didn't do anything special just for the coast. Whereas, because the climate in where I grew up on coastal Southern California is like totally different than El Paso. I mean, there's nothing similar about it except for it's warm most of the year and kind of cool because it's also dry. So, I guess the similarity factor is that it's really dry in both places. So
this might pull out some more detail.
It might.
Because you got a lot of the coast influencing those coastal areas.
So anyway, what I was getting at before is, I'll upload some of these data sets, and you could, if you wanted to, even practice doing the training part. So with this data set, you could actually find an area and label everything as being in one class or the other class, and then run it. Like you could specify some alpine climate, and then run it and see what else it chose for other alpine climates. Okay. So yeah, now we have more, and it picked a different size. I kind of liked it when it was the other size. So it's easier to see. Yeah, I think one thing I'm going to do is just make. So if I go more and say for my all symbols, I can go to properties. I can make these a little bit bigger, and it'll make it a little bit easier to see. So, well, we've gotten a few extra ones. So now we get a little bit, the southern coast. So this is a similar exercise to what people would have done to come up with climate zones.
Oh yeah, like the farmer almanac and planting zones and stuff.
Yep. So here, look at that. Red is really interesting now. So the red area is just the kind of marine west coast climate, it looks like, and so it gets really different in precipitation. This is the precipitation. So the precipitation is really high in the winter. It gets pretty low in the summer, and then goes really back up in the winter. Okay. So it has this pattern of climate, and you know that's true. That it's cold. Those areas, it's colder in the winter. Now in Southern California, that also happens, but I guess on a smaller degree. So it looks like it's mostly pale pink. So you still get that wet winter, drier summer, It's pink. See right here? Oh yeah, you can't even see it, but
Yeah.
it dips down
Yeah,
and
I
comes back
kinda,
up.
I can kind of see
It doesn't have as dramatic of a difference, but it still has that the drier summer. It goes back up a little bit and then goes back way up.
So is that the mid-range of all the numbers?
Yes, that's the mid-range of all the numbers for that particular.
Oh yeah, I can see if I peek on your.
Yeah, it's hard. I don't know how. Maybe I could change the background. But other climates like the blue up here, which is kind of the middle of the United States, most of Texas, that actually gets wetter in the summer, and then but it's always warm. I would look at the Marine West Coast climate. The red goes down, up, but the temperature, it gets a little bit cooler. Actually, it looks like in the summertime temperatures, and goes back up. But it's almost always really moderately cool.
Our coast has almost the opposite, just not as extreme. The yellow mustardy, the top yellow one.
Yeah, the yellow one.
Yeah, not the bright yellow, the mustard.
Yeah, mustard yellow. This one.
The one up.
Oh, this one.
Mm-hmm.
Yeah, that's ours. Yep. So it gets way wetter, and it gets
Stays pretty warm.
yeah, stays pretty warm.
Except for today out. It's cold.
Yeah. Actually, I think I might have these reversed. Right. This might be. I mean, it's still having that same pattern where it gets wetter, or maybe it gets hotter. I think it gets hotter in the summer. But why would it get way cooler in the summer? This must be. I think I was right the first time. That must be temperature, and this must be precipitation. Or precipitation and temperature. Yeah, like that area gets significantly warmer. Precipitation doesn't change as much, I guess, as temperature overall. Okay, so that's the analysis, and like I said, there's no lab for today. I was going to make a lab, but I didn't get around. I had a big meeting yesterday that I had to get ready for, and this is a new lecture, so I didn't do that. But if anybody has any questions on your assignments, your final assignments, we can do that for the lab. I just want to take like a 10-minute break. I need to go to the bathroom.
Okay, so how's our meeting going to be next week? When we come in next week?
When you come in next week, it's going to be like a review session like we did before.
So come with all of our questions for labs and stuff. And
Yep, and then
anything about the exam.
the lab will be similar to today, but it'll be up. I'll be up there to help them with their finish off any labs that they have. So if you guys have any questions on labs, it'd be good that you want me to be here personally. We can always do it through Skype, but if you want me to face, then I can definitely help out.
Well, you'll
I'm
be doing
here.
IBM, though. You'll be doing IBM if you got any questions.
Yes, I'll do IVNs, and anytime you can do it via. Because sometimes it's easy. Because with Skype, you know that like.
You can take over the screen.
Yeah. So right now I'm tied in with Ben, and he can see my screen. Now I don't know if Ben wants to show me his screen right now, but he could. Like so right now, you can click on this little. I think. Do I have to stop sharing? I have to stop sharing probably. So if I stop sharing.